Hello students, today we will discuss about the some properties of dislocation which we have studied in the previous lecture. So there were two type of dislocations, one was edge dislocation and another was the screw dislocation. Now as I told you before, the dislocation is a distortion along dislocation line. So just above the slip plane, they are in the state of compressive stresses, and just below this slip plane there are some tensile stresses. So the total energy associated with one dislocation, we call it distortional energy, is represented by E equal to half of mu b square. E equal to half of mu b square, where b is the Berger vector and mu is the shear modulus of that material. Now this dislocation energy, there is one thing which is written here, that dislocation tend to have as small as Berger's vector as possible. What does it mean? Let us suppose you have a crystal which is having one dislocation, right? One dislocation. So the energy associated with this is E equal to half of mu b square. The another one, let us suppose you are having that material is having kind of two dislocations, right? So its energy will be, for this again, half of mu b square, and here is the half of mu b square. Now if in another case the two dislocations are together like this, so the Berger vector associated with this will be 2b. So the energy E equal to half of mu 2b square, right? Half of 2b square. So whenever this is the case, because every materials want to be in an equilibrium state, energy is high, distortion is high, so they always also want to remain in the equilibrium state. So what happens, they split like this to reduce their distortional energy. So initially, so it comes out to be E, in this case the E equal to 2 mu b square, E equal to mu b square. In this case, if it is splitted in two separate dislocations, then in this case will be half of mu b square plus half of mu b square equal to mu b square. So there is a 50% reduction in the distortional energy. So that's why dislocation tends to have as small as Berger's vector as possible, just to remain in the equilibrium state. So if you see the dislocations, you can have a positive edge dislocation here, you can have a negative edge dislocation. So in the positive edge dislocation, there will be a compressive stresses, there will be a tensile stresses. Now if it is a negative, here are the compressive and here are the tensile, and here is the compressive. So the opposite sign dislocation attract each other during the any shear forces, and we call it annihilation of two dislocations. On the other hand, if you have the same sign dislocation, they tends to repel each other because they are having the same sign. So more distortion energy, they try to repel each other. In the same way as the double dislocation, two dislocation, these has splitted in this way to keep their energy, distortion energy minimum, which is 50% less than the two dislocation parallelly together. So this is something very important to understand, the Berger's vector, because you can have a simple cubic, body-centered cubic, face-centered cubic, and some ionic solids. Each material is having its own Berger vector, which is an invariant quantity. Now you see, when a dislocation is moving, they always move along the most close spec, in the most close spec direction. So if you have a unit cell, you must have studied this in the crystal structure chapter, the line density and the plane density. So this is the FCC 110 type direction, which is the most close spec. So dislocation will move in this direction. Preferential direction is the close spec direction. Or I can say, let us suppose this is a river or some kind of a gap. You are two cases. Here you are finding a step in between. Here there is a no step. So if you want to cross it, you will prefer this path. You will not directly jump, given a choice. Same way, if the one direction is like this could be 110 for FCC, and if it could be a body diagonal in the case of BCC, which is 111. So this is the close spec direction. So when I talk about the Berger vector is basically interatomic spacing. So this is the Berger vector in this case, and this is the Berger vector in this case. Means half of 111 direction in BCC, half of 110 direction for FCC, and if you have a simple cubic, then this is A equal to 2R. This will be the Berger vector, and this direction is 100. So these are the Berger's vector for monoatomic crystals or crystal structure. For NaCl, for kind of as a ionic solids, then dislocation cannot be anion to cation. It will be anion to anion or cation to cation. So these are the Berger's vector for ionic solid. So as I discussed before, so this is the BCC, this is the one direction half of 110, and here this is in the case of simple cubic. So in ionic crystal, as I told you before, there is an extra plane of atom contain an atom of one type, right? So in this case, CSCl, which is basically, if you see the CSCl crystal structure, I don't know whether you have studied in the structure of solid or not. CSCl, here is the CS atom and here are the Cl atom. So the Berger vector is not this. The Berger vector is this. Same way in the NaCl, the Berger vector is half of this, because NaCl structure basically is a FCC structure like this, and here are the sodium, these are the chlorine, this is the sodium. So this is not the Berger vector. The Berger vector is this face centered, half of this again face centered. So you can say also, because there is a presence of cation also, so one can say for ionic crystals, Berger vectors are generally large as compared to monoatomic crystals.